we have studied about index properties, particularly soil grain properties and their grain size distribution. In the grain size distribution, we have introduced two methods. One is for coarse grain soils, that is based on the sieve analysis, and for fine grain soils we have introduced a method called hydrometer analysis. In this class we try to learn about the measures of the gradation, and we will try to classify the soil based on the gradation, and if this procedure is not adequate for classifying the fine grain soils, we will introduce a method for classifying the fine grain soils, that is based on the consistency of fine grain soils. So, this lecture is with title Index Properties and Soil Classification Part 2. The measures of gradation, as we discussed in the previous class, the percentage finer is plotted on the y axis and particle size is plotted on the x axis on the logarithmic scale. Basically, different sizes are used for getting the or analyzing the grain size distribution curve. This is a typical grain size distribution curve is shown here, and different particle sizes are represented here: D10, D30 and D60. D10 is known as the effective particle size and D50 is known as the average particle size. D10 means, which is termed as effective particle size, is doesn't mean it means that 10% of the particles are finer and 90% of the particles are coarser than that particular particle size D10. That means 10% of the particles are finer and 90% of the particles are coarser than the particular particle size D10. Similarly, D60 means diameter of the soil particles for which 60% of the particles are finer and 40% of the particles are coarser than D60. That is what it means by D60. So, we use typically D10, D60 and D30 in arriving at measures of gradation. Some commonly used measures are the uniformity coefficient. The uniformity coefficient Cu is defined as a ratio of D60 by D10. So, when the Cu is defined as D60 by D10, if the value of the Cu is say less than 4, they are considered to be poorly graded or uniformly graded. When Cu is greater than 4 to 6, it is understood as a well graded soil. So, if the value of the coefficient of uniformity or uniformity coefficient is greater than 4 to 6, then it is actually understood as a well graded soil. If the value of the Cu is less than 4, considered to be poorly graded or uniformly graded. In the sense, uniformly graded in the sense have got identical size of the particles. For example, for desert sands, Cu will be approximately equal to 1. Coefficient of gradation or curvature, another coefficient to measure gradation is Cc is equal to D30 square divided by D60 into D10, where coefficient of gradation or coefficient of curvature is D30 square by D60 into D10. If the value of the Cc ranges from 1 to 3, then it is understood as a well graded soil. So, for the soil to be well graded, the value of coefficient of uniformity has to range in between, has to be greater than Cu 4 to greater than 4 and Cc in the range of 1 to 3, then the soil is said to be well graded. So, if you look into this, higher the value of the Cu, the larger the range of the particle sizes in the soil. So, if the Cu value is high, that indicates that the soil mass consists of different ranges of the sizes of the particles. If the value of the Cu is large, indicates that the soil mass consists of different ranges of particle sizes. Engineers frequently like to use a variety of coefficients to describe the uniformity versus well gradedness of the soils. engineers frequently like to use a variety of coefficients to describe the uniformity versus well gradedness of the soils. Let us consider a grain size distribution curve which is shown in this slide. Percentage finer by weight on y axis, particle size d represented on the logarithmic scale on x axis, and this is a typical curve is shown. These different points are obtained by performing sieve analysis. So, here as we said, D60, D10 and D30 can be worked out like this. For example, D60 is taken here as 0.7 mm. D60 is read from the curve as 0.7 mm. Similarly, D10 is read from this curve as 0.12 m. 0.12 mm. D10 is equal to 0.12 mm. D60 is equal to 0.7 mm. D30 can be found out from here, that is here, from here we can find out that D30 as around 0.3 mm. So, if you find out the coefficient of uniformity here, D60 by D10, that is the ratio of D60 by D10 is works out to be 5.8, and D30 coefficient of curvature is D30 square by D60 into D10 gives to around 1.07 or so. So, this indicates that this particular typical grain size distribution curve represents for a well graded soil, because the value of the Cu is greater than 4 and Cc in the range of 1 to 3, that indicates that the soil is a well graded one. In that case, it represents the particles with different ranges. Particularly, these curves are plotted on the logarithmic scale, because these grain size distribution curves are typically plotted on logarithmic scale because of the by keeping in view of the different ranges of the soil particles. The soil particle size can range from 20 mm down to less than 0.002 mm. Keeping this in point of view, to represent the different sizes of the soil particles, we generally represent these grain size distribution curves on the semi logarithmic scale. Let us look at the particle size classification. Based on the grain size, once we get different gradation of the different particles, then we will be able to classify the soil based on their particle size. This is the table which shows the particle size classification as per ASTM D2487. This is a code in ASTM which talks about the particle size classification. So, here in this column, a sieve size is given and particle diameter and the soil classification. So, different types of the sieves are indicated. For example, here this particular is retained in the 12-inch sieve, that means that the particle diameter is greater than 300 mm, it represents boulder, and which passes 12-inch sieve and retained in 3-inch sieve, that indicates that the particle diameter ranges from 75 to 300 mm, which represents cobble. The sieve size which is passes 3-inch and retained in 0.75 inch represents that particle diameter ranges from 19 to 75 mm, which is a coarse gravel type. So, similarly, when you come down, we see which is passing through number 40 sieve and retained in 200 sieve. That means that the particle size ranges from 0.075 mm to 0.42 mm, which represents the fine sand. Below this, that is passing 200 mm sieve, passing to number 200 sieve, that means that less than 0.075 mm particle size represents the fines, that is silt and clay fraction. So, if you look into this here, the sizes from 19 down to fine sand, they are treated as coarse grained soils, and these soils which are fines are treated as the fine grained soils. That means that from soil particle size ranging from 0.075 mm to 975 mm diameter, basically it is considered up to 19 mm, treated as coarse grained soils, and fines which are passing 75 micron sieve or number 200 sieve, they represent fine grained soils which consists of silt and clay fractions. So, typical characteristics of the GSD curves, if you look into it, suppose it is possible for us to get different types of the curves with a different steep with inclinations or a slopes of the grain stage distribution curves. So, if the curve is steep, that is steep curves, steep grain stage distribution curve, it indicates that the value of the Cu is low Cu values and is a poorly graded soil. That is, low Cu value or poorly graded soil means it indicates that the soil mass consists of identical sizes of the particles, and as we discussed earlier, it is very difficult to compact identical sizes of the particles. So, the steep curves indicate low coefficient of uniformity or uniformity coefficient values and a poorly graded soil, and which is also known as uniformly graded soil. So, Cu is less than 5 for uniform graded soils. Flat curves in the sense which is extending from the larger particle size to finermost particle size indicates that higher Cu values, which indicates that is a well graded soil. So, flat curves they generally indicate well graded soils. Most gap graded soils have a coefficient of curvature outside the range. So, we have introduced like a gap graded soil, sometimes in absence of the intermediate particle sizes exists. So, with this what happens is that that particular type of soil is called gap graded soil or bimodal soil. Most gap graded soils such as a CC outside the range. So, let us look now in the terms of GSD of soils a problem. The previous class we have introduced like a problem wherein we took a weight of dry soil for the sieve analysis as 500 grams, and it sieved through different sieves of sizes 4.75 to 75 micron sieve, and it represents the grain diameter here in this column, and weight retained in the each sieve, and this is the cumulative weight retained in the each sieve is calculated, and the cumulative weight passing is given by the cumulative weight passing is 490 grams is passed through the sieve, only 10 grams is retained here. So, 490 by 500 into 100 it gives you 98%, that is the percentage finer by weight, and which is actually first point on the grain size distribution curve, and with ordinate y equivalent to 98% and x in the terms of particle size as 4.75 mm on the logarithmic scale. Similarly, once we get this, we will get as a percentage finer by weight. Once we plot percentage finer by weight on y axis on arithmetic scale and the particle diameter on x axis on a logarithmic scale, we will get a typical grain size distribution curve. So, in this case once we plot, then we will get the typical grain size distribution, we will get the typical grain size distribution curve. So, let us look now, as we noticed that only 20 grams of soil passed through 75 micron sieve. So, to calculate the percentage gravel, that means that gravel size particles which are greater than 4.75 mm. So, percentage gravel is calculated in a soil mass which is you let us take the particle size greater than 4.75 mm. So, 100 minus 98 then it gives you 2%. It indicates that 2% of the soil mass have got a gravel size particles that is greater than 4.75 mm. Similarly, percentage coarse sand ranging from 2 mm to 4.75, percentage medium sand 0.425 to 2 mm, percentage fine sand ranging from 0.075 mm to 0.425 mm, which gives us percentage coarse sand as 33% and percentage medium sand as 37% and percentage fine sand as 24%. So, percentage silt clay fraction is that is sizes having particles having sizes less than 0.075 mm, which is 4%. So, which is less than 12%. So, as we discussed, the hydrometer analysis is not generally recommended if the percentage of the silt clay fraction is less than 12%, and if it is more, then it is required to be determined and then incorporated in the grain size distribution curve. So, having obtained this percentage gravel and percentage sand and percentage silt and clay fraction, then we can determine different coefficients which are used for measuring the gradation. So, coefficient of uniformity can be obtained by D60 by D10. So, here the D10 is determined from the grain size distribution curve as 0.13 mm and D30 as 0.5 mm and D60 as 1.8 mm. So, by determining now Cu works out to be 13.8 and Cc, which is D30 square divided by D60 into D10, works out to be 1.1. As Cu is greater than 6 and Cc is in the range of 1 to 1.3, 1 to 3, the soil is said to be a well graded soil, these coefficients are these particle sizes are obtained from the graph. So, this is the soil is well graded. Now, it is once we complete this analysis, we say that soil is well graded with percentage gravel 2%, percentage sand 94%, percentage silt clay as 4%. So, here to revise once again, D60 is nothing but 60% of the particles are finer and 40% of the particles are coarser than D60. So, this is required to be remembered while determining the these particle sizes from the grain size distribution curve. So, this is the typically how we solve a typical problems how we analyze the grain size distribution curves. So, in this slide a typical example which is not the same whatever we have seen just now, but this is another example in which a typical grain size distribution curve is shown, where the particles ranging from sand, silt and clay and which is plotted with effective particle diameter, the particle diameter on x axis and percentage finer weight on y axis. So, if you determine here the percentage gravel is 100 minus 100 is 0, the percentage sand is 100 minus 60, that is around 40% is sand, and the silt is around 60 minus 12 which is 48% and the clay is around 12%. So, this is basically the soil with major amount of the soil is with the fines and then some sandy soil. So, it is something like a silty sand type. So, sand is sandy silt where clay is where the sand is less compared to composition of the silt and clay. Time to time these grain size distribution curves also can provide an indication about soil's history. As we have studied from the origin of the soil can be a residual soil or a transported soil. So, in the case of a residual soil, let us consider a typical grain size distributions of residual soils collected at different ages of the soil. So, here this particular type of this particular particle size distribution curve represents for the young residual soil, and this one is the intermediate maturing soil and the fully maturing soil. So, as you can see from the young residual soil type 2 intermediate maturing to fully maturing, there is a gradual change in the particle sizes can be noted. So, a residual deposit has its particle sizes constantly changing with time as the particle continues to break down because of the certain process of weathering. So, a residual deposit has its particle sizes constantly changing with time as the particles continue to break down. So, this is a typical grain size distribution curves for the residual soils, where we have seen a young residual soil deposit, an intermediately maturing soil deposit and a fully maturing soil deposit. As we run down, we see that a residual deposit has its particle sizes constantly changing with time as the particle continues to break down. So, we can say that the GSTs can provide an indication of soil's history. So, this can lead to and give a conclusion about the soil's history in the past. Let us consider a typical grain size distribution curve for transported soils. Here a grain size distribution curve for a glacial type soil and a glacial and alluvial soil can be seen. So, river deposits may be well graded, uniform or gap graded depending upon the water velocity, the velocity with which the particles are being drifted, and the volume of the suspended solids and the river area where the deposition occurred. So, the river area where the deposition occurred or the volume of the suspended solids and the water velocity. So, as you can see with glacial to glacial alluvial, the soil is undergoing the particle size distribution of the particular soil is getting changed. So, this is also a typical example of the grain size distribution curve for the transported soils. So, this particular slide shows typical grain size distributions of different soils. So, let us see here different soils have been represented here, percentage pioneer by weight on the y axis and particle diameter on the x axis. You can see here this curve indicates a typical grain size distribution for a gravelly sand. So, indicates that if you see here the large amount of the particle size which is more than 4.75 mm is gravel, and then which is followed by sand. So, we can say that there is a composition of soil mass is gravel, that is certain percentage, and sand, predominantly sand, then we call it is a gravelly sand. So, this particular grain size distribution curve is shown for silty fine sand. You can see here there is fine sand particles, and composition also has some silt particles in it. So, this particular curve represents for the silty fine sand, and this particular curve represents for clayey sandy silt. Clayey sandy silt because silt is predominant over the clayey and sandy soils. So, in that way it is called as a clayey sandy silt. So, major portion of the soil here is silt, and these two curves show a different grain size distributions of the flocculent and dispersed kaolinites. Flocculent and dispersed kaolinite. So, dispersed kaolinite is finer, and flocculated kaolinite is in the silt size, and dispersed kaolinite is shown to be observed to be in the finer range. And this is the typical grain size distribution curve of sodium bentonite, that is montmorillonite. The montmorillonite has got you can see the finest particle sizes. That is what we have learned from the while introducing structures of the soil minerals. We said that the bentonite has got the finest of the finest particles with highest specific area and highest cation exchange capacity. So, this is this slide represents typical grain size curves for the different soils. In this slide, particle size distribution of the bentonite, illite and kaolinite are shown. So, as we learnt in the previous lectures, and kaolinite is supposed to have large particle sizes compared to illite and then bentonite. The similar thing can be seen here, which is represented after Koch 2002 as this is the kaolinite particle size distribution curve, and this represents illite clay, and this is the sodium bentonite. So, sodium bentonite is observed to be the finest among bentonite and illite and kaolinite family. So, having learnt about the measures of the gradation, let us try to understand or see what is the significance of this grain size distribution curve, that is the practical significance of why we are required to determine the gradation of soils, that is the practical significance of GST, that is grain size distribution. So, GST of soils smaller than 75 micron, that is with the passing 200 number sieve, is of little importance in the solution of engineering problems. GSDs larger than 0.075 mm, that is 75 micron sieve, have several important uses. So, GSD affects the void ratio of soils and provides useful information for use in cement and asphaltic concretes. So, the grain size distribution curve affects the void ratio of soils. We have seen that if the soil is well graded, the void ratio is supposed to be less, and if the soil is uniformly graded, the void ratio is supposed to be very high. So, GSD affects the void ratio soils and provides useful information for use in cement and asphaltic concretes. So, well graded aggregates requires less cement per unit of volume of concrete to produce denser concrete, and less permeable and more resistant to weathering. So, if you have got information from the grain size distribution curve and a well graded aggregate has been selected and which requires less amount of cement per unit volume of concrete to produce a denser concrete and less permeable and more resistant concrete surface for the weathering. So, this is one of the practical significance with the grain size distribution analysis. The second significance, a knowledge of the amount of the percentage of fines and the gradation of the coarse particles is useful in making a choice of material for base materials under highways, runways and rail tracks. So, basically in highways and runways it is utmost requirement to give a mechanically stable foundation to support the loads which are coming onto the pavement. So, for that we are required to have the matrix with certain amount of the fines. So, a knowledge of the amount of the percentage fines and the gradation of the coarse particles is useful in making a choice of material for base courses and highways and runways and rail tracks. And another practical significance which we will be discussing later is that to determine the activity of the clay based on the percentage of the clay fraction. That means that based on the percentage clay fraction, we can say whether that particular clay, that is the clay soil with particles finer than 2 micron is active or inactive, or in what extent it is active. All these things can be said by determining the activity, which is possible with the percentage clay fraction. And to design filters, basically number of filters are required either to provide drainage in case of parking lots or road subbases and all. And in case of retaining walls, basically the filters are designed, or along the canal banks the filters are designed. So, to design filters are used to control seepage, and pores must be small enough to prevent the particles from being carried from the adjacent soil. So, basically the criteria for designing the filters is to see that to control the seepage, and the pores must be small enough to prevent the particles from being carried from the adjacent soil. So, let us look into this particular requirement for the practical significance of the grain size distribution curve with reference to retaining wall, that is a filter material adjacent to a retaining wall. Basically a filter is required to be provided behind the retaining wall to get rid of the water pressure, because once the wall is getting the effect of the water pressure, then the lateral pressure exerted on the wall increases. To get rid of the pressure from the water which is collected behind the wall, it is required to provide different ranges of filters, a coarse filter or a fine filter and a backfill soil. And then to drain the water from here, either a collection pipes can be kept here, or it can be kept with holes which are called as weep holes. So, for there are certain criteria for selecting the filter material, basically for retaining wall. The D15 of the filter soil, that is the D15 of the filter material, the ratio of D15 of the filter to D15 of soil should be within 4 and 20. Another criteria which is required to be satisfied is D15 of filter to D50 of soil should be less than or equal to 25, and D15 of filter to D85 of soil shall be less than or equal to 5. By fulfilling this criteria, one can design a different types of filter materials, and the filters can be designed basically to see that the backfill material, the fine particles in the backfill materials are not required to be washed out. Only the water which is there within the backfill soil is required to be drained, so that the wall is free from the lateral pressure exerted from the water. Similarly, this criteria for selecting the drainage material is followed in Indian Roads Congress 37 2001. The criteria works out to be as follows. For the pavement structural section, because the functional performance of the pavement depends upon the drainage of the water. So, the life of the pavement depends upon the drainage which is there at the subgrade level. So, for that which is required to provide the drainage material. So, to design the drainage material, it should be seen that ratio of D15 of drainage material to D15 of subgrade should be greater than or equal to 5, or and D15 of subgrade and D85 of subgrade should be less than or equal to 5. And one more criteria which is there is D50 of drainage to D50 of subgrade shall be less than or equal to 5. So, these two criteria are basically to prevent entry of soil particles into the drainage layer. So, these two criteria are basically selected or required to be fulfilled to prevent entry of soil particles into the drainage layer. For good drainage materials, basically it is required to be seen that D85 is less than the 4 times the D15. So, for good drainage materials, D85 shall be less than or equal to 4 times D15, and D2 shall be greater than or equal to 2.5 mm. That means that the drainage material this indicates that D85 of a drainage material shall be less than or equal to 4 times the D15 of drainage material, and D2 of drainage material shall be greater than 2.5 mm. Then we can select this particular material as a qualified drainage material in the case of a pavement structural section. So, another practical significance is to estimate the coefficient of permeability of the coarse grained soils. Hazen has tried to find out coefficient of permeability of the coarse grained soils basically using the effective particle size D10. Number of correlations have been found out, and it has been documented that for determining the coarse grained soils, basically sandy soils, this particle size D10, that is effective particle size, is used to determine the coefficient of permeability of soils. That is, the permeability is nothing but ease with which the water can pass through the soil matrix. And also the another significance is that to assess the frost susceptibility in soils based on the percentage clay fraction. Basically, this frost susceptibility is required to be high for the fine grained soils, that is particles passing 75 microns sieve or so, or particles having less than 2 micron size. So, to determine that, the reason for this particular phenomena is that whenever the water in the voids within the sand is frozen, then what happens is that if the water contained in the voids of a saturated clean sand or the gravel freezes, the structure remains unchanged, because there will not be any much expansion, because freezing merely increases the volume of each void by 9% in coarse grained soil, because the expansion of water is contained within the void itself. So, because of that they are not more susceptible, whereas in case of fine grained soils the water which is prevalent in the voids increases, and it causes heave, which is called in case of a clay soils as frost heave, which is because of this particular nature. So, to assess the frost susceptibility of given soil, a fine grained soils, we are required to determine the percentage clay fraction. By assessing that, whether we can find out how much this frost susceptible the soil is. So, some applications of the GSA in that is grain size analysis in geotechnology and construction is the selection of fill material. So, we wanted to select a fill material for constructing embankment or for constructing earth dam. In the case of earth dam, different gradations are required in the different zones. So, the selection of fill material is important, where the gradation will come into the picture, because the for certain type of constructions you are required to have a well graded materials to contribute to the strength. And road sub base material, as we said, to provide the mechanically stable foundation, we are required to have a good knowledge about the grain size analysis of the particular material under consideration. And to drainage filters, basically it is required to be known the drainage characteristics of the filter material with the adjacent soil characteristics. And groundwater drainage, So, and grouting and chemical injection. Suppose this is a phenomena to strengthen the ground or to fill the voids in the ground or to fill the voids or cavities in the ground. This grouting is a phenomena which is used by a chemical injection or a cement sand grouts are inserted into the into the ground. So, to work out this, it is required to know the knowledge about the this grain size analysis. And the concreting materials, we have seen that in order to produce a denser concrete, you need to have a well graded mix, so that the less amount of cement or asphalt can be consumed. So, the more denser is the concrete, the more resistant it is to the weathering. So, dynamic compaction. So, this is another phenomena to compact the soils. So, for this also the knowledge of the grain size analysis is required. So, in the summary, let us look into it. We have seen that a coarse grained soils which is greater than 75 micron is analyzed by using the sieve analysis, subjected to the soil mass which is placed in the series of sieves and subjected to shaking, and while measuring the percentage retained and by calculating the percentage cumulative weight of the soil retained in each sieve, percentage finer weight can be calculated, which is plotted here, and which based on that we can say the soil is different coefficients can be found out, and then we can be said that as a well graded or a uniformly graded. So, uniformly graded, it looks like the particles are of equivalent size, and you can see that this curve, which is a steeper curve, which represents a uniformly or a uniform poorly graded soil, and this represents a well graded soil because the finer particles are filling the voids within the large particle sizes. So, this is a well graded poorly sorted soil type. So, coefficient of uniformity here we said is that Cu is equal to d60 by d10, and coefficient of curvature as d30 square divided by d60 into d10, and we also said this effective particle size is indicated as d10, indicates that 10% of the particles are finer and 90% of the particles are coarser than this size, and we also said that d50 is the average particle size. So, for the particles which are finer than 75 micron, it is required to find the particles by using the hydrometer analysis, and depending upon the sizes of the particles they settle, and then hydrometer is required to be worked out with different corrections to get the fine particle size percentages, and once it is corrected, it can be joined with the original grain size distribution curve to get the complete curve. So, this hydrometer analysis is required to be carried out if the percentage finds is more than 12% or so. So, having seen now basically having determined the particle size of a coarse grained soil, to some extent we are able to classify the soil, but we also have the soils with major amount of soils, major portion of soils with passing 75 micron sieve, that is very fine soils. In that case, we need further information to classify these fine grained soils. So, for that we consider the physical states of soil. That means, if you look into this slide, here a different types of soils are shown. A gravelly soil is shown here with the different particles of different particles sizes, and a sandy type soil is shown here, and a clay type soil can be shown here. As can be seen here, with water, with less amount of water, this particular shape can be attained. By adding more amount of water, this particular lump of soil you are seeing, it may lose its shape. So, different physical shades are possible with fine grained soils, and what leads to a consistency of a given soil. So, for classifying the fine grained soils, let us, before classifying the fine grained soils or before introducing the classifications of fine grained soils, let us introduce a term called consistency. So, the consistency of fine grained soils is generally is defined as the property of a material which is manifested by its resistance to flow. So, it represents the relative ease with which the soil may be deformed. So, degree of the firmness of a soil and is often directly related to strength. This is basically represents the degree of firmness of a soil. Generally, it is conveniently represented like this. We say that fine grained soil of soft consistency, or medium consistency or medium stiff consistency or medium firm consistency, all are alike, and stiff or firm or very stiff. So, these terms unfortunately are relative and higher have different meaning to different observers. So, but this is a relative explanation of the different physical states with different consistencies, like soft, that is said to be soil may be having very low strength, and medium stiff and very stiff soil. In soil mechanics, it is needed to determine the range of the potential behavior of the given soil based on very few simple tests. So, typical concerns are the following. What will happen when the soil is having less amount of water or more amount of water? That basically we are referring for the either coarse grained soils and fine grained soils. Soil might shrink or expand excessively in an uncontrolled manner after they have been placed in geotechnical structures, roadways upgrades, dams, levees, foundation materials. Or soil might lose their strength and ability to carry loads. So, in case of different states, typical concerns for the geotechnical engineers are soil might shrink or expand excessively in uncontrollable manner after they have been placed in geotechnical structures such as roadways upgrades, dams, levees, foundation materials. Soil might lose their strength and ability to carry loads safely. So, tests used to detect the potential problems for coarse grained soils, basically gravel and sands, are different from those used to detect the potential problems for the fine grained soils, basically silts and clays. So, coarse grained soils, basically water content is generally not a major factor. For coarse grained soils, water content is not generally a major factor. Major factor leading to shrinkage is the structure of the soil skeleton. That means that the arrangement of soil particles or soil fabric can change from the loose state to the dense state. That is only in the case of a coarse grained soils is possible. So, major factor leading to the shrinkage, in the sense in the sense of coarse grained soils indicates that a loose fabric can change to a dense fabric or very dense fabric. Fine grained soils, the water content is a major factor. So, water content is a major factor. If you see here, as the water content increases from left to right, soil expand and lose in strength. As the water content decreases from right to left, soil shrink and gain in strength. So, if you look into this, fine grained soils are prone to get affected with the presence of water. So, that is an interesting phenomena, and Atterberg, a Swedish scientist, basically for agricultural purposes has come out with certain limits of water contents at which the soil changes its physical states. So, that is being currently used to determine these limiting water contents at which the soil undergoes the physical states, and which are used for, these limits are used for determining or classifying the fine grained soils. So, as we have studied earlier, it was discussed that fine grained soils have higher specific surface areas, because the finer is the particle size, higher is the specific surface area, and electrical charges, they are supposed to have higher electrical charges around the surfaces on their particles. Because of this, fine grained soils and clays in particular can change their consistency quite dramatically with changes in water content. With the availability of water, the consistency of the soil can be changed from the firm to soft state or a very stiff to soft state. So, each soil type will generally have different water content at which it behaves like a solid, semi-solid, plastic and liquid. Different states have been introduced, like solid, a solid state, it is like a brick type, and a semi-solid, plastic and liquid state. For a given soil, the water contents that mark the boundaries between the soil consistencies are also called as Atterberg limits, after Swedish soil scientist A. Atterberg 1902. So, here onwards we will see how the Atterberg limits are defined and how they are reduced and how they are determined. So, that and all we will be looking into the further course of the lecture. So, here as mentioned here, the consistency of the fine grained soils is given here. The soil with a solid state, that is the limiting at this interface between the solid state and semi solid state is indicated as a shrinkage limit. That is, the interface between solid state and the limiting water content in between solid state and semi solid state is indicated or termed as shrinkage limit, and limiting water content between semi solid state and plastic state is indicated as a plastic limit, and limiting water content between plastic state and liquid state is indicated as a liquid limit. So, these liquid limit, plastic limit, shrinkage limit, they are known as Atterberg limits. So, Atterberg limits are nothing but water contents where the soil behavior changes. So, here solid to semi solid state there is a change in behavior, semi solid to plastic state there is a change in behavior, and plastic to liquid state there is a change in behavior. Mostly the natural soil deposits, they do occur at very close to plastic limits, in this range of the very close to plastic limits. So, let us consider this particular curve which is plotted with water content on the x axis, volume of sample on the y axis, water content on the x axis, volume of sample on the y axis. So, where this shows the different transition stages from liquid to solid stage, transition stages from the liquid to solid stage, where let us consider a different transition points like A, B, C, D and E and F. So, here V naught is the initial volume of the soil mass, and Vs is the solid, Vs is the volume of the solids, and Vw is the water. That means that here the volume of water is many times more than the volume of the solids. So, V naught is the initial volume of the soil mass, that is above the liquid state. So, if the soil is allowed to dry, then it undergoes changes from liquid state to plastic state to semi solid state to solid state. So, you can see here the limiting water content between the liquid state to plastic state is indicated as a liquid limit, which is indicated as WL, liquid limit. If you are indicating the liquid limit in percentage, it is called it is indicated as W suffix L, or if you are writing the value of the liquid limit, then is indicated as LL, liquid limit. Similarly, at point C, semi solid state, interface between the semi solid state and plastic state is known as the plastic limit. So, the difference between liquid limit and plastic limit gives the range of the plasticity of the soil, that is liquid limit minus plastic limit will give you a plasticity index. And once you allow the soil to dry up to point D, then you can see that upon further drying the soil mass will not experience any change in the volume. So, there is from point D to F, the curve undergoes this particular zone is said to be a transition zone. When it is changing from semi solid state to a solid state, the curve is not linear, it is in the curvilinear shape. So, it is said that one of the possible reasons for this phenomena is because air starts entering from this point. So, this is the point where air entry starts and then it comes up to this point, and then here by this time mostly the water is replaced by air, and the soil grains are pressed so close that there will not be further reduction in the volume. So, even upon the further drying, even if you keep it in the oven, the soil mass will not further reduce in volume, because the particles have been pulled close, such a close distance, such a way that there will not be any further reduction in the void ratio. So, and at different levels, for example, at A here the volume of initial volume it represents here, and here it represents the volume of the soil mass at point B, and the corresponding this point represents the water content corresponding to this state. Here this curve is supposed to be inclined at 45 degrees, because if the gamma W is around 10 kilonewton per meter cube, the volume change of the soil at any point during this process, when you allow drying from A to D, the volume change of the soil is equivalent to the volume of the moisture lost. So, this point B is the limiting water content between the liquid state and the plastic state is said to be a liquid limit, at point C is the limiting water content between plastic state and semi-solid state is said to be a plastic limit. So, the difference between liquid limit and plastic limit is indicated as a plasticity index, and a limiting water content at point E is indicated as shrinkage limit. So, shrinkage limit is the minimum water content at which still the soil is completely saturated. Afterwards, the soil is transforms or undergoes change in color. So, that indicates that the drying is taking place, or the change of the color indicates that the water is being replaced by air. So, here the evaporation of the soil where air starts entering. So, this is the entry point, and then here completely it enters and replaces all the water which is there in the voids. So, if you extend this curve further down here, this point gives the volume of the solids. The volume of solids which is constant throughout in this process of drying. So, this slide shows the different states of the physical states of the fine grained soil, that is interface between liquid state and plastic state is defined as a liquid limit, and the interface between semi solid state and solid state is defined as shrinkage limit. Interface between plastic state and semi solid state is defined as a plastic limit. So, as we defined, let us look into the definitions of Atterberg limits. So, liquid limit is the water content at which a soil is practically in a liquid state, but it has infinitesimal resistance against the flow which can be measured. So, at liquid limit the soil has practically a small shear strength which can be measured. So, most of the soils have the shear strength at liquid limit is around 2.7 kilonewton per meter square. So, a liquid limit is the water content at which the soil is practically in a liquid state, but has infinitesimal resistance. Above liquid limit, the soil state changes into a slurry state. And plastic limit is the water content at which the soil would just begin to crumble when rolled into the thread of approximately 3 mm diameter. So, the plastic limit is with the same definition or the same phenomena. By using the same phenomena, we determine the plastic limit of a given soil. So, plastic limit is the water content at which the soil would just begin to crumble when rolled into thread of approximately 3 mm diameter. Shrinkage limit is the water content at which a decrease in water content does not cause any decrease in the volume of the soil mass. So, even at the shrinkage limit, the degree of saturation is said to be 100%. So, if you wanted to determine void ratio at the shrinkage limit, we can say E shrinkage limit, the void ratio at shrinkage limit is equal to water content at shrinkage limit is nothing but the shrinkage limit times specific gravity of the solids. Similarly, for void ratio of a given soil at liquid limit, EL is equal to WL into GS, while void ratio of soil at the plastic limit indicated as EP is equal to WPGS. So, Atterberg limits provide a good deal of information on the range of the potential behavior of the given soil might show in the field and variations in the water content. So, this particular behavior is shown here with when the soil is solid, that is stiff or very stiff, semi solid, plastic and liquid. So, these interface limiting water contents here is given as a shrinkage limit, plastic limit, liquid limit, and here it shows that a solid, the soil is hard and brittle. The stress strain behavior, suppose if you take a sample which is pressed with a certain stress sigma, a compressive stress sigma, and with a strain, axial strain epsilon, then soil experience or exhibits a brittle behavior if when it is hard. When it is during the semi solid state, the soil has combined brittle and ductile behavior like a stiff cheese material. It has got a combined brittle and ductile behavior, and when the soil is in the plastic state, soil has very ductile and malleable behavior. So, in the plastic stage, soil has very ductile behavior and malleable behavior, and in the liquid state, that is soil behaves like a thick or a thin viscous fluid. So, almost the soil is having zero strength. So, here liquid limit is the point where the soil still possesses an infinitesimal shear strength which can be measured. Normally, this shear strength of the soil at liquid limit is said to be around 2.7 kilonewton per meter square. And we also define the plasticity index is the range of the moisture content over which soil exhibits plasticity. So, plasticity is defined as the property of a material which allows it to be deformed rapidly without rupture. So, the plasticity is very important for the fine grained soils, which is defined as the property of material which allows it to be deformed rapidly without rupture or without breaking. So, IP, the plasticity index, if it is indicated in percentage, or if it is indicated in values, it is indicated as PI, as liquid limit minus plastic limit. The greater the difference between WL and WP, greater is the plasticity of soil. So, this is an important parameter while selecting different materials for the construction. So, in this lecture, we have studied about the measures of the gradation, and then also we introduced to a consistency of fine grained soils and different physical states of fine grained soils, and we introduced Atterberg limits, and we defined them as liquid limit, plastic limit and shrinkage limit, and these Atterberg limits are used further to classify fine grained soils, and we will be using these Atterberg limits to classify the fine grained soils. And in the next class we will try to look into different classifications based on the plasticity index of classifications of soil based on the plasticity index, that is Atterberg limits, and their intricate details pertinent to Atterberg limits and their determination.